Okay. So the present candidates for multiplexing techniques are very advanced, and sometimes some of them are not well proven. Okay. So uh, it will take a while for new technologies to take over. Okay. Anyway, I'll first discuss the solution of our class test. The class test has been scary. It has been a nightmare for you guys, right?
So I'm not sure until I get the marks.
Oh, really?
This after the marks, I'll get the nightmare.
I think once you get the marks, it will be even worse. I mean, worse than your expectation. Okay, it's not only nightmare. Okay, your days will even be marred. Okay. By the way, can you hear me?
Yes, sir.
Okay. Uh, so let us discuss the solution. Then you'll realize that most of you have been wrong. Actually.
So
Um,
have you finished marking all the papers?
no, I haven't. I haven't. I have had a quick look at some of the answers. Okay. First, let me discuss the problem with the OVSF codes. Okay. Uh, well, you had 128 users, and they all are, I mean, at the spreading factor, I mean, 128. So they all are at the same level of spreading factor. So when I want someone to be a lower spreading factor, okay, lower than the present one, then of course I have to go to an upper level in the OVSF code tree. I'm so sorry. I was trying to fix my writing pad. It's not working. Um, things are giving me trouble. It's not working, and uh, anyway, uh, maybe I have to take it to the university to some experts. Okay, so when you go to an upper level, then the branches, okay, you see if you go one step upper, then from and one step upper level, you had two branches. So instead of two, you can get one user. If you go two step higher level, then uh, I mean, there could be instead of four people, you can allow one guy to use the resource. Okay. So it's actually two to the power your levels. Okay, and the same ratio by the same ratio you reduce the number of users, right? So if it is three levels higher, then two to the power three. So I mean, instead of eight users, two to the power three. So instead of eight users, you get one guy to use the resource. Okay. So now I think you can take care of the problem easily. So there are like, if I consider the largest spreading factor with the new ones, then it is 64. Then it is 64. So that is just one level higher. So instead of two users, uh, you get one. But you have, I mean, the question says that you have in the new allocation three users with the spelling factor 64. So this change will take place for three sets, meaning that 3 into 2, you reduce 6 people and add 3 people. Okay, instead of 6 people, you allow 3 people with the spelling factor 64 instead of spelling factor 128. Let me know if anything is unclear.
Can you
Then,
demonstrate a bit? So
do you want me to repeat?
it's hard to understand getting these statements. Then it's a bit confusing.
I sorry, I could not hear you well.
It's a bit confusing.
Uh, okay. I mean, you're saying that it's confusing.
Sir, if it was possible for you to demonstrate sharing the screen, then it would have been better.
Yeah, I wanted to. I was trying to fix my writing pad. But it's not. It's creating problem for me. I don't know. I don't know what the problem is, but it's connected to my computer. But for last couple of weeks, it has been a part of the display comes in. The taskbar is shown, but not the rest of the. Uh, I'll check once again just with the software. Okay. You don't see any lines, right? Do you?
No, sir.
No, sir.
Yeah. I'm not sure what the problem is, but Oh, okay. If you want, I will work more on it and discuss the solution in the next class. If it is really unclear, okay.
Okay, sir. So what was the answer for that math?
77.
Okay, sir.
Now the first question. You have, most of you have been wrong. Well, that we discussed in one class that the I mean, several times we mentioned that in the CDMA environment, the I mean, like in the party, the people who are speaking in other languages uh, are not directly a problem for you, but they work like some background noise. So it's not like you don't have any problem from there. It will be problematic if they use higher level of sound. Then you have higher background noise. So it's like whiz noise. Okay. So the higher the uh, number of users with other languages, or if you have people in other languages with higher level of sound, you have higher level of background noise, and that will degrade your performance. Okay. So in fact, your data rate will be affected when you have other people using higher power. So for when the users are close to the base station, they can use low level of power. But as they go far, okay, either in downlink or uplink, the level of power requirement goes higher. Okay, because say in the downlink, the base station has to use higher power so that the users can now hear. In the uplink, the UE has to use higher power so that the base station can now hear. So now for any guy, it finds more higher amount of power in the cell as its background. So the background noise increases. I mentioned in one class that the capacity is not exactly fixed with the OVSF codes. Rather, it also depends on this background noise. Okay, rise over thermal. I said that there is a measurement of how much noise, background noise, there in the cell, and it is called uh, rise over thermal. How much the background noise power above the thermal noise level. Okay. So that is called ROT, thermal rise over thermal. So depending on that, I mentioned then that although the number of voice users may be close to 100, but it is in CDMA network, it is not fixed. It rather depends on this noise level. It's not like you have some cores and you can then allocate. Well, now if you allocate the cores, the noise is already enough high, so the noise will be even higher. So you may not allocate the cores. Okay. So actually, uh, you you have lower capacity. The capacity degrades. The capacity degrades as you have higher level of power uses, and that happens when the users go towards the cell edge. So it's about the own cell. Now about the adjacent cells, the effect is also worse. Well, when you are getting closer to another cell, okay, you are getting towards the cell edge, and so you are getting closer to another cell, then also, say if I talk about uplink, so the other base station can now receive your power. I mean, that's not your serving base station, that's the base station in a different cell, but that base station now receives significant power from you, which is like the background noise, which is like a background noise. Okay, so the other people whoever are using that cell will find your power level with the background noise. And it's also true for downlink. In the downlink, you are receiving power from your base station, but your base station is using high power, and uh, the users in the other cell will receive power from your base station too. I mean, significant power from your base station. Okay, it's not only the base station from its own cell, but from your cell too. Okay, so it's a uh, uh, it's a I mean it's worse for all of them. Now let me tell you, this is actually a general condition or general impact. Okay, in any general technologies, if you have the users closer and closer to the base station, then you have better and better capacity. Okay, and as the users go further and further towards the cell edge, the capacity degrades. It's more problematic situation for the radio engineers. Okay. If it was the case that all users were always very close to the base station, then the radio problem would be the easiest. Okay, but that's not the case. So I mean the users are scattered, and so they have to deal with the practical complexities. Uh, so anyway, and although we did not discuss, let me also mention we did not this part. So no, I don't expect that you will answer in terms of code rate or packet rate transmission. But let me tell you that in CDMA network or I mean in MTS, okay, you have a fixed modulation. In its later version, HSDP or okay, you have different modulation levels, but in original UMTS you have just one modulation level, QPS. But the code rate is not fixed. There are different code rates, and so as you go further away, the code rates are reduced. Also, the packet rate transmissions increase. I mean, because of higher background noise, higher background noise. Okay, so the capacity just goes lower and lower. It is adversely affected. Okay. Now, the third question, do you have any questions on my answers? Okay. If not, I will quickly go over that OVSF code tree problem. I will try to fix the writing pad and come back to you with the explanation, drawing it. Okay. But let me tell you that you had the users at 128 spreading factor. So say if when you have two users using 128 spreading factor, you you could allocate the resource from these two guys to one user at 64 spreading factor, because a spreading factor node, okay, I mean at 64 user, the OVSF code at the spreading factor 64 can have two branches with spreading factor 128. So instead of two guys, you can allocate the resource to one guy at 64. Now in the problem, you had three users to be allocated with spreading factor 64. So two people you can sacrifice from 128 and allocate 64. Another two people and another two people. So six users you can drop from 128 and you can allocate three people at spreading factor 64. So minus 6 plus 3. Similarly, there are one user to be allocated spreading factor 32. So that is one step higher. So you could allocate there 4. Okay, I mean 32 have two branches with 64, and again two branches at 124. So there are four. Instead of four people with 128 spring factor, you could allocate the resource with 32 to just one guy. So you need one guy with 32. So you subtract 4 and add 1. Then 16. Okay. From 16 to 128. Okay. It's a, I mean, 16 times 8 is 128. Okay. So you can, I mean, so 8 people you can cut down and add one guy with 16 factor 16. Okay. Because 8 times you have. The ratio is 8. 128 divided by 16 is 8. But there are two people, so 2 into 8, 16 guys you have to drop from 128, and you can add two guys with the spin factor 6, 16. Finally, one guy with 16 spin factor 4, so that's a ratio of 32. Okay, 32 between 4 and 128. So cut down 32 and add 1. So you have uh, uh, so in total you subtract 6, 4, 16, and 32, and then you add 3, 1, 2, and 1. So that gives you 77. Okay. Okay. I think I should remove the writing pad because it's making things slow for me. Okay. Then question number 3: how many PSCs are possible? 512. And this number of PSCs have been used because you need to make sure that the PSCs are not repeated in close vicinity in the radio network. Okay, because the you has to distinguish the different cells when it identifies. So the, I mean, signals must not come to the UE with the same PSC. Okay, and but if you make it too high, then the uh, I mean, if you make it unnecessarily high, then the correlation will degrade unnecessarily. What are the achievements after completion of step 2 in step 1, 2, 3 procedure? In step 2, you get two things. I mean, in terms of time alignment, you get the alignment with the radio frames, and also in terms of synchronization. I mean, cell identity information, you get a reduced search space for the PSC. From 512, it reduces to 8. Okay, you know that the PSC must be one of these 8. Okay, so these are the achievements of step 2 in step 1 to 3 procedure. Okay, now I'll discuss our LT. Okay, a few things I have little updated. Okay, I just thought it would be better to have. Actually, when I shared the uh, network architecture for LT, I told you that I would give you that whole uh, picture. Okay, so now I've added that, but with some 3G 2G information too. Okay, I mean the first slide, introduction of LT, is now added with little bit information of 3G, 2G first. Okay, the network.
Sir,
Yeah, yeah.
sir, the way you explain the answers of the quiz questions, so is it possible for you to give us some practice questions beforehand so that we can think the topics in that way? Because in the quiz, for the first time, we thinking like your explanation is pretty hard. So if you give us some practice questions, so we can think like that and implement the exam.
Okay. Okay. Well, actually, I prepare on one side. I prepare questions before a test, and you can get midterm and final questions of the last year. Okay, this course was also offered in the last year, and also before that there is a course 4613 in which in the second part of that course I used to cover LT. Okay, I mean the two courses, wireless communication, this cellular communication, wireless communication, these two things are merged in one course then. The number course code 4613. So you can find some questions there that should help. Okay, and we will. Okay, let's see. Uh, we can discuss a few things here and talk about some probable questions. Okay, so let's see. It is already, you see, it is already now difficult with this uh, online method of our assessment to assess you with fair judgment. Okay, so I have to create questions that that enables fair judgment, and so that's why I have to create questions like that. Okay, but of course, it in this first attempt it has been tougher than I thought of. Okay, somehow I made it a little tough. I didn't not realize that. So anyway, let's see. On one side, we have to take open book exam. Okay, so that's it. So with these conditions, uh, I mean, sharing, our discussion maybe, and some through the discussion we may talk about some questions. Okay, that probably can be the best thing. Okay, okay, let's see. Now, in the case of 3G, I told you before that the UE is connected to different base stations called Node B, and then they are connected to RNC, and this whole part is RAN, UTRAN. Okay, in the case of UMTS, it is called UTRAN, the RAN part, and in the core network, there are two paths, but the paths are not like control signaling and data. It's not like that. The Since they support CS and PS, one path, the top path supports CS and the bottom path supports PS. So it is divided between CS and PS. So when you have CS calls, like voice calls or SMS for this type of routing, this MSC and then GMSC, gateway MSC. So that is that, and here is JSON is like a router which routes the IP packets. Okay, and gateway is a number of, you may have a number of MSC in the, like Grameenphone. I don't know how many pieces they have now. They had before in Dhaka 8 or 9 MSCs. Okay, So what all these MSCs have mesh connections. The MSCs have mesh connections. One of the MSC is GMSC, Gateway MSC, which takes data outside Grameen network. So similarly, Ruby have a number of MSCs, but one of the MSCs are Gateway MSC, which takes data outside Ruby. So these gateways are connected. Now there is ICX2. So Gateway MSC is connected to ICX from any operator. Similarly, GGSN connects to the ISP. Okay, CS domain MSC, and VLR is, I mean, you have the subscriber information. Okay, like, I mean, what we call HSS in 4G was called HLR before 2G days. Okay. Uh, the same thing they have mentioned. Okay. So connections between RNC was allowed. Oftentimes there were connections between RNC, but there were no connections between node Bs. Between node Bs, there were no connections. Okay. If you have both 2G and 3G, sorry, if both 2G and 3G, then in the case of 2G, it's called BTS, and I mean it's called BSC, base station controller. So I mean they all are connected to the same core network components: MSC, GMSC, or SGSN, GGSN. Now in the case of 4G, we know how it is. We already discussed. So this SGSN is connected because I mean it's also part of PS network. Okay. So you may have this one is from my book. Okay, I mean this one I drew with Visio for my book. So this shows all different types of connections, paths. Okay, and the dotted lines are optional. Okay, these connections are optional. So this is one set of option, and you see there is another type of dotted line. There's also another option. Okay, this connection also you may have, and this connection. So if you have these additional connections, then there are some advantages. Okay, especially for uh, say when you do CSFP, you switch calls, you switch to 3G network for the voice call. Okay, then it takes place in two different ways. If you have a connection, direct connection, then it is quicker. Okay, if you have this S12 connection, then it takes the advantage of this connection and it is quicker. And if you don't have the connection, then it takes place little differently. CSFB occurs little differently. Okay, I explained in my book in chapter 21 how it takes place when you have CS12 connection and when you don't have. Okay, but now you see that there are connections between E node Bs now, between E node Bs. But of course, you can also have connections between MMEs. It's called S10. So all the connections have all the interfaces have some terms, some names are there. Okay, and EPC, I mean, you have core network and you have radio network. So this one is radio network, EUTRAN. Okay, and this is your core network, but the core network is called EPC, Evolved Packet Core. Like before, they called CN. You see, CN, core network, radio network system. These terms are radio network system or RAN, or the radio network system are the terms for this part. And for this part, it was CN, UTRAN, and CN, core network. but now they little more smartly call EPC, Evolved Packet Core. Okay, this is what I added here. Just one last thing. Uh, System frame number. We know that the radio frames, each 10 millisecond long, okay, appear one after another in time. These radio frames are numbered. Okay, all these radio frames are numbered, and it is called system frame number, SFN. Radio frames appearing one after another in time are numbered sequentially. Okay, so it's a 10 bits long number. So after you wrap up the whole string, 10 bits long sequence, then you restart. Okay, again from 000, you restart the numbering, uh, and these numbers are broadcast. Okay, on every alternate radio frames, the network broadcasts the number. Okay, it's a broadcast on some information. Okay, system information message. It's called master information block. We'll look at the system messages later, but one of them is MEIB, or master information block, which includes the system frame number, SFN. Okay, but the point is all is radio frames are numbered sequentially. Okay, if something is 472, the next radio frame will be 473, then 474. Okay, this is what I added for to that previous slide, and I also added just couple of slides to PCFICH, although I mean this addition wasn't very important. But it will probably take just a couple of minutes to. We know that PCFICH remains on the first symbol, but this shows that how they are. Okay, in fact, I mean here, here horizontally we are showing the frequencies, and vertically the time. So the first symbol takes of the PCFICH. They are just located this way, taking 4 resource elements, but at 4 different locations. It is spread in the frequency. The subcarrier for the first group is, if it is K, then the second one will be K plus 1/4 of the total number of subcarriers, then K plus half of the total number of. So you see that this resource element groups for PCFS, this all these groups together form the whole PCFSH information, and that is just spread at 4 different places. This information is spread at 4 different places. Okay. And also this K depends on the PCI. Now we know what PCI is. Okay, it's a function of PCI. So different cells will have shifting in the frequency by different amount in the neighborhood. Okay. So you don't have, there's a better coordination of interference among the cell, intercell interference coordination. It is called ICIC, intercell interference coordination. So that is better when you have different, because on PCFICH you may have significant power on every cell, but they occur at different frequencies in the neighborhood. So you may not expect uh, any destroy of this resource elements, or the UEs will hopefully be able to decode PCFS, because it's very important that you are able to decode. If you fail to decode it, then you cannot proceed. Okay, right in the beginning, you are blocked. You cannot process anything else. Okay, so PCFS is the whole control information part is important. The control region may have higher level of power for transmission. Also, they are made robust in different ways. Like BCFACH is made robust. If you lose even one part of them, okay, it may be able to recover. And that's the point why they have split it into different frequencies, because uh, in the radio environment, different people, there are different uses at different frequencies, and sometimes there may be high level of power at some frequencies. So those frequencies are for that moment, or for a transient period. Some frequencies are have high, I mean, worse condition, high level of interference. Okay, the point is, I mean, different cells may use different level of power, different frequencies, and somehow, uh, I mean, if the management is not good, you may have unexpected high power level at some frequencies. That really happens in the cellular network. I mean, it's not, this interference doesn't come from other sources, but from your own cellular environment, from other cell, or sometimes even your own cell. So anyway, so frequency diversity means when you split your data and spread it at different frequencies, and interleaving or something you use such that if a part of it is damaged, okay, uh, so there is some burst error or some burst interference at somewhere, so the rest can allow you to retrieve the data. Okay. So this for the same reason, this is split into 4% spread. Okay. So this is called frequency diversity. I wrote it somewhere. This provides for frequency diversity spread within the whole bandwidth using the subtle numbers. Okay. Okay, this is what I added. Oh, I have like half an hour. Now we were discussing the different identities from the UE end. And we showed that the UE has a large identity, very large, GUTI, okay, which also includes a part from its MME, the MME which is currently handling the UE, or which has allocated the GUTI. Okay, so that MME has included its own identity here, and only this MTMZ part it allocates differently to different people. Okay, now um, when the UE say you have no calls up, but you are receiving a call, so the network then looks for you. The network sends a message or broadcasts a message in the cell that this particular guy, I'm looking for this particular guy, please respond to me. But how does it do that? It has to send the identity of the user in the over there message, that I'm looking for this guy. So that message has to include the identity of the you whom it is looking for. What that ID? What will be that ID? Well, that ID could be ideally IMSI, right? Because IMSI is what is used for your, I mean, identity in the cell. But the problem is IMSI is fixed for a user, and it may happen that some eavesdropper uh, has come to know your IMSI. Okay, so in the wireless signaling, he keeps checking when there is some paging message. I mean, the network looks for someone with this IMSI, and then he keeps when he finds that, he starts tracking, and then he steals some information. So this is why IMSI is usually not used in the over-there messages just for security purpose. Rather, the network, uh, I mean, this GUTI is a temporary identity, and the temporary identity used, but the GUTI is very long. So a shorter temporary identity is created, and that is STMC. Okay, taking only these two parts, STMC is created. So that is it. Okay, so GUTI can be allocated when you first power up. So that is initial attachment with the network. Also, when you go to some other area or even at your own place, uh, after some time period, at some regular intervals, GUTI will be reallocated. So since IMSI is a permanent identifier, as I said, this STMC is used in the over-there messages. Okay. Paging message is the one that the network uses to look for when it looks for someone. Okay. The users have no sessions, data sessions up. The network needs to knock someone, so he sends a broadcast message. Okay, that is called paging message, that I need this guy. C-RENTI, I mean, the industry people call it RENTI. This is another identity allocated if you have some data sessions up. Okay. So there are basically two different states for the UE. When you have some data sessions up, then you are in a state called RC, connected state. And if you don't have any data sessions, no voice calls, or no, you're not doing any browsing, you're not downloading anything, so you are idle, you have no activities going on, then you will be in idle state. So this, I'm writing down these two states for the EV: RC, idle state, and RC, connected state. So just these two states depend on whether or not you have some activities, some data transfer going on. Okay. So when you want to do data transfer, first you need to move to RC connected state. Then you begin the data transfer. And as soon as you move from RC idle state, as soon as you move to RC connected state, your cell will give you an identity, which is called CRNT. And that's a identity, I mean, cell specific. Cell is specific. If you move to a different cell, then there'll be handover, and you'll be allocated a new CRNT. So CRNT is cell specific. Whenever you move to different cell, uh, you will be allocated a new CRNT. Whereas GUTI or STMC is not cell specific. In idle state, you may be moving around. The network is not updated with your current position, and you will be you'll have the same GUTI. You'll have the same STMC. So STMC or GUTI doesn't change. It changes once in a while, okay, but not when you change your cell. But CIDENTity is cell specific identity. It changes when you change the cell. I think I have mentioned it somewhere. It doesn't look like. Then I will add. Yeah, it is at the cell level. Okay. Unique identification of the U at the cell level during RC connected state. P-Renti is sorry. Uh, this thing we may discuss when we discuss the paging. Okay, I mean when the we looks for the users. First, it uses before it sends the paging messages in the control region. It sends a PDC instance with P-Renti, and then everybody knows that there is some paging message to come in here. They all read, and in the paging message it says that I'm looking for the network says that I'm looking for this and this person giving their estimates. Okay, but okay, P-Renti we'll discuss later when we discuss paging. Okay. Uh, Now in this current discussion, I mean in the in my next discussion, a few slides will be repetition from our previous course. I actually added them as reminders, okay, and to complement the whole discussion. Well, I mentioned this term already, but formally I'm not showing you that. Say on the transmitting side, I have different layers. Layer 2, layer 1. Layer 2 has different sub layers. Okay, so uh, data comes from the application layer and it goes to about next bottom layer, then next lower layer, although it comes to the bottom layer. Now, when it is for received by a layer, okay, from the upper layer, then it is treated as service data unit or SDU, and the particular layer works on this uh, packet of data. It may add some headers or tails. Okay, so it may sometimes split the packet into several packets. Whatever it does, after the actions, it creates new packets, and these packets are then called PDU, Protocol Data Unit, and then they are forwarded to the next lower layer. The next lower layer receives those packets which were PDU for the upper layer, but now the next lower layer treat them at SDU for itself. Okay, I mean the PDUs of the upper layers are SDUs for the lower layer. Okay, I mean upper lower. I mean for the same layer. Okay, so if any so say for example RLC is a layer. On top of that, on top of RLC you have PDCP. So when PDCP receives layer data from upper layer, they treat them as due. But when PDCP delivers, these delivered packets are PDUs for PDCP. But PDUs for PDCP layer are SDUs for RLC layer. Okay, that's for transmitting side. Similarly, from the receiving side, you receive uh, PDU from the lower layer and create SDU for the upper layer. Okay, so it's an opposite direction of flow on the receiving side. The physical layer first receives and forwards it to MAC layer, MAC forwards it to RLC, RLC. Probably you forgot these names, so maybe I show you the names again. PDCP RLC. Okay, so PDCP creates which are SDUs. For RLC, they are PDUs, and then creates PDUs, they are SDUs for RLC, and SD creates PDUs, they are SDUs for MAC. MAC creates PDUs. Okay. Okay. Any questions? If not, then this slide I already covered in the last semester, but just as a reminder, this slides also I covered. This one probably I also covered. So you have two methods: forward error correction (FEC). I mean that's actually coding, turbo coding or conventional coding or whatever you use, and then packet retransmissions. It's an additional. The packet retransmissions occur at different layers. You see, for RLC, MAC layer performs packet retransmissions, and it tries to correct. When say even after coding, you find that in the receiving side, the packets have not been received correctly. Then you let the transmitting side know. The transmitting side will retransmit the packets. So it's packet retransmission. That's not, that's adding some load to your radio resources, but you have to receive correct packets. So MAC layer tries to correct them. If MAC layer fails to correct, then its upper layer will take over and try to correct. That's RLC. If RLC can do this same packet retransmission, it can also do. If it also fails, then TCP layer will try to correct. For TCP, the retransmissions you may already have covered in the last semester in the other course. In a different course, you have learned probably how TCP performs retransmissions. But in the lower layers, it tries to fix. Okay, if it fails, if it can correct at lower layers, then it will be more efficient. However, the correction methods are a little different. In RLC, it is ARQ, like TCP. TCP is automated repeat request. Okay, RLC has also ARQ, but little differently it is used. But it is ARQ. But in MAC, it's a different version. It's not exactly ARQ. It's called hybrid ARQ, HARQ. So this HARQ is a combination of FEC and ARQ. What it does, when it finds that, well, the data block is not correct, I haven't received the correct one, it does not discard the data block, it keeps that. Realizing the fact that all the bits in the block are not incorrect, some of them are still correct. Okay, so, and if I receive a retransmitted block, that may not be perfect too. Some bits may still be in error. So why not try to combine these two and get a correct one? So it says when it fails to retrieve the correct. Of course, HARQ actually works in combination with further correction with the coding technique. That's why HARQ technique varies depending on your coding technique. Okay. But the bottom line is that first with the data block, it tries to recover using the coding, but if it fails, that then tells it reports to the transmitting side that I haven't received, I was not able to recover, so send me again. So the second version of the data block is sent, and that may not have again all bits correct, but it soft combines. It didn't discard the old one, it soft combines and try to recover now correctly. If it fails again, that tells the transmitting side that send me again, and tries to recombine again with using all these three, and then again fourth. So there's the uh, last limit. It allows retransmissions for the third time, and it attempts to retrieve the data combining all four, the original one and the three retransmitted blocks. Okay, so that is HARQ. So soft combines bits from the previous attempt with the current retransmission. So that is a more advanced technique, but RLC and TCP are straightforward. Okay, if you fail, then you transmit the whole packet again. Okay, and if you can correct at the lower layer, okay, I will talk later little more about HARQ. Okay, it has two types: incremental redundancy, HS combining. Okay, I'll talk little more about that later. For now, let me tell you that if you can correct at lower layers, then it will be more efficient. First of all, you can correct more quickly. Like for example, if there is a mistake somewhere in an office, at there is a hierarchy in the office. At the lowest level, there has been some mistake. If the lowest level people can correct it, and it is not propagated to upper layer officer, then it is more quickly solved. If the upper layer officer comes to know, then it will be, he manages many more people, okay, and it will be more time consuming for him uh, to correct. And if it goes to even higher level, then it will be even more time consuming. It propagates to that level, and that level is busy with larger things. Okay. So the data packets are larger at upper and upper levels. So if you can correct at the lowest level, then a smaller data block, first of all, at the lower layer it is solved. So the problem is not propagated to upper layer, and it is more quickly solved. Secondly, also if it propagates to upper layer, then say RLC data blocks are larger. Okay. From the transmitting side, you visualize RLC forwards it to the MAC layer. The data block from RLC PDU, when it comes to MAC splits it into a number of blocks. So the MAC PDUs are smaller. So if a MAC PDU, when the MAC PDU MAC level you resolve, then MAC PDUs will be retransmitted, not RLC. So that will be retransmission of smaller data blocks. So your bandwidth will also be saved in retransmissions. But if you solve it in the RLC level, so a number of MAC PDUs are combined. So maybe a particular MAC PDUs you could not resolve correcting in MAC layer. So the upper layer RLC sees that in this RLC packet, which has four MAC packet, it is not correct. But that's because just one MAC packet could not be corrected. But RLC will retransmit the whole packet, which includes all four MAC PDUs. So that will be a larger block of retransmissions, consuming the bandwidth more. Okay. So overhead will be more, and it will be more time consuming. It will not be that quicker. Um, okay, and also, in terms of that acknowledgements, okay, when you signals the other end that I need a correction, okay, it is not correctly received, that will also be higher as the problem propagates to upper level. Anyway, we are close to the end of our slot and we have to finish quickly because we need to catch the Asr prayer. Questions?
Sir,
Yep.
do you have the soft copies of the previous year questions?
I'll see. I'll try to find out.
If it is with you, then you can just directly share it in the drive. That will be more convenient because like most of us don't have access to the library right now. Like we are not in IIT.
Okay. Okay. I'll see if I can do that.
And sir, is it possible to, I mean, like previous semester we did a scanned PDF upload in Google Form. Here we did typing explanation. So like, is it possible to go back to scanning the PDFs or sending you the pictures in WhatsApp? Because
Yeah,
like,
actually, that I did not forbid. I mean, you could do that too. Okay. So in Google Classroom, you can also upload. And so from next time, um, I thought this time it will be, I mean, that would not be a requirement. But of course, we can use that. Okay, you can just upload in the Google assignment. Okay, so you can scan and upload. Okay, anyway, you should be able to submit. It should be okay.
yes, sir, if you could add an
But
optional upload.
you know, there are, I mean, few things will be like selecting multiple choice. Okay, for those things you just select. For the rest, from next time I'll allow you to scan and upload.
Yes, sir, you can include multiple choice and short questions, but for some big mathematics which needs like diagrams and all sort of stuff, we can't just simply type it.
Hmm.
So if you can enable the option to upload,
Yeah, yeah,
that would be great.
yeah. I mean, this time it's not like that. Uh, I I thought that that would not be required. But if you ask for it at the time of the exam, I definitely allow you to do that. Okay. I would have allowed. Okay.
Okay, sir,
If
we were not really aware of that
yeah.
in the middle of the exam.
So anyway, um, from next time, inshallah, you'll be able to do that. Okay. Okay. Jazakallah for your time. Uh, we're okay. We need to catch the Asr prayer anyway. I'll see you tomorrow, inshallah.
Okay, Assalamu alaikum, sir.
Walaikum salam.